Hi, this is Mrs. Dalberg. Welcome to AP Chemistry, and today we are practicing with some free response question for our unit on periodicity, electrons, empirical formula, a whole smorgasbord of stuff. So let's get started. Practicing these free responses will definitely help you out on the tests, and especially that big test in May. So if you look at your worksheet, there are some other years that have a question. If you feel like you need extra practice, go to those years and those question numbers and kind of look at that. That's your extra practice if you need it. But for now, we're going to look at question number 2 from 1998. So question number 2 in 1998 is a combustion analysis, which is a fancy empirical formula problem. And they have an unknown sample that contains carbon, hydrogen, and oxygen, and a pure sample is analyzed and found to be 65% carbon. We have 9.44% hydrogen, and we want to know the empirical formula of the compound. And so setting that up, we have 3 elements. Finding the empirical formula is really just finding the mole ratio of those 3 elements, carbon, hydrogen, and oxygen. And so if we look at that, the carbon is 65.6%. The hydrogen is 9.44%, and oxygen is the rest of it. And the rest of it means if you take 100% minus the other 2, you get the percentage of oxygen that's left, which is 24.96%. So if you know percentages, we don't know grams. Assume you have 100 grams, and so you have 65.6 grams of carbon, 9.44 grams of hydrogen, and 24.96 grams of oxygens. Now, step 1 is to find the moles of each of those and compare the mole ratio. And so if you look at this, divide this one by the molar mass of carbon, which is 12.01, we get 5.462 moles. If we do that for hydrogen, hydrogen is 1.01, and we get 9.37 moles. And for the last one, for oxygen, oxygen has a mass of 16.00, and if we divide that, we get 1.56. Okay, now we have the number of moles, and if we want to know the ratio, pick the smallest number and divide all of those by that number, and that gives us a ratio that's maybe a little bit easier to compare. And if we look at this bottom one is 1. So for every 1 oxygen, we will have 6 hydrogen, and we will have 3.5 carbon. So that's our ratio of moles. So to write the empirical formula, we can't have a fraction, so we would have to double everything. So if we double all of those, we have carbon. We have 7 moles of carbon for every 12 moles of hydrogen, and then for every 2 moles of oxygen. And so that is our empirical formula for this one. That is 3 points. 1 point for finding the number of moles of both of these. 1 point for getting the moles of oxygen. And the last point for the empirical formula. And so that's how the points are awarded in this question. Okay. Now the next question is from the year 2006. Again, it's another combustion analysis problem. And we have a 1.2359 gram sample is burned in excess oxygen. So oxygen is excess. And we formed 2.241 grams of carbon dioxide. It also showed that the sample contained 0.0648 grams of hydrogen. And so the first question is asking us to determine the mass in grams of carbon in the sample. Okay, and so if you look at that, I don't really know too much from that, except I start with that sample. The only thing I know about carbon is that when it's burned, carbon dioxide is formed from the carbon, and all of the carbon forms this. So if I know how many moles of carbon dioxide I have, I can figure out how many moles of carbon I had. And then if I know how many moles of carbon, then I can figure out how many grams I started with. And so starting that line of thought, if I know how many moles of CO2, I need to start with how many grams of CO2 that I have. And I have 2.241 grams of carbon dioxide. And I know that for every, what is that, one mole carbon dioxide, I have a molar mass of 44.01 grams. Okay, and that will give me the number of moles of carbon dioxide. And I can just, in the same T-chart, I can do one step here, or I can just keep going. I know for every 1 mole of CO2, I had 1 mole of carbon in my sample, and if I know the number of moles of carbon in my sample, for every 1 mole of carbon, I have 12.01 grams of carbon. And so all in one step, I can figure out how many grams of carbon were in my sample. And the number of grams is 6116. And let's look at that. I'm going to double check my sig figs, and if I started with this number, I should have 4 sig figs in my answer. I'm good. That is worth 1 point. Okay, the next step was to figure out on part 2, it's analyzed for nitrogen only, and the mass percent is found to be 28.84%. Determine the mass in the original sample. Okay, so if I start with a mass of 1.2359 grams of the sample, and the percentage of nitrogen is 28.84%, I can just multiply that by 0.2884. That's the percentage in the sample. And that tells me the percent of nitrogen by mass. So I end up with 0.3564 grams of nitrogen in our sample. Okay, so now we know the grams of carbon, the grams of hydrogen. This was also just worth 1 point. Determine the mass of grams of oxygen in the sample. And so, I'm not sure. It says we have excess oxygen, but I know that I have the mass of carbon in my sample. I just found that here. I know I have the mass of nitrogen in my sample. Just found that there. They also gave me the mass of hydrogen in my sample. So if I know the mass of my sample, all I have to do is subtract everything to get the mass of oxygen. And so if I have the mass of the sample minus the mass of, we'll just start with the carbon, minus the mass of the nitrogen, minus the mass of our hydrogen, which is up here, we have 0.0648 grams of hydrogen. And so everything that's left is our oxygen. And so when we subtract all of those, we get this number, 0.2031. And it should have, to do the math on this, if you have 4 places past the decimal when you subtract in each of these, our answer should have 1, 2, 3, 4 places past the decimal. Okay, and this answer is also worth 1 point. Now, you just have to be consistent with your previous answer. So, for example, you can still get all your points on number 3, even if you got number 1 wrong. If you had the wrong answer for part 1 and you plug that wrong answer in here correctly, this answer would look different, but it would still earn full credit. So it's not a double jeopardy thing. If you do this step wrong, you only miss that point here, and you have to use your answer consistently here. Okay, last step, to determine the empirical formula of the compound. And so if we look at that, the last step is to take all of those masses and convert them to moles to get the ratio of moles. So if I look at carbon, I have 0.616 grams. If I divide that by 12.01, I get 0.05092 moles. If I do hydrogen, looking at that one, I had 0.0648 grams of hydrogen, and the molar mass of hydrogen is 1.01, and so that gives us a molar mass of 0.06429. Do nitrogen next. Nitrogen had a mass of 0.3564 grams, and it has a molar mass of 14.01, and that gives us 0.02544 moles of nitrogen. And our last one is our oxygen, which is in the last step, 2.2031, and the molar mass is 16.00, and if we divide, we get 0.01269 moles of oxygen. So now we have the ratio of all our moles, and actually this is where the last point is awarded. So if you only got to this step, you would get full credit for all the points offered in this problem. But our last step, which may be worth points, sometimes it's not, is to figure out the mole ratio. So if we pick the smallest number and divide all of those by that smallest number, and our smallest number is our oxygen, 0.01269. Oh, actually, we don't. We do have points for the rest. So you would get 4.013, 5.066, 2.005, and 1. Okay. And so you got a 1 point here for dividing by the smallest number of moles. And then the last point is for finding the ratio or writing the empirical formula consistent with all your other answers. So if your empirical formula is wrong, that's fine. It just has to be consistent with these answers. And so if we look at that, these are all in a 4 to 5 to 2 to 1 ratio. So we can write C4, H5, N2, and then O1. So this is our empirical formula. Okay. Okay, moving on. Now we are in 2008, and we are doing a gravimetric analysis that is somewhat similar to our lab that we did. And so if we look at this, we have some data. It's a gravimetric analysis, and gravimetric means that you had a solid formed, and you use gravity to remove some of the water. You then took it and dried it, and you found the mass of your product and used that to find out information about your starting materials. And so if we look at this, in this case, we had magnesium chloride. Now, magnesium chloride is a hydrate, which means that there are waters of hydration associated. And so if you have magnesium chloride, this little dot means that there are some number of waters associated with that crystal. And when you heat it, those waters come off, and in an environment like Louisiana where it's kind of humid, all these waters will reassociate with this lattice crystal structure, and water will actually be incorporated in there. And so the student got the mass of their empty container, and then they put their sample in. And so the difference between those would be the mass of the sample. Now, if you look, this is the mass of the sample and container after the first heating. Now, what is this? If you subtract this from the empty container, you would get the sample minus these waters of hydration. So minus a certain number of moles of water, depending on the number of moles you have of your sample. Now, if you look at that, when they heated it a second and third time, if you look here, the mass became less. And then between here and here, aren't those exactly the same? Not exactly, because out 3 decimal places, we have one number that's different, but the mass didn't change there. And so if we look at Part A asks us to explain essentially what we just noticed there. It says, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. And so if you heat it and you check the mass, and you heat it and the mass decreases like it did between the first and second, that means you still had waters of hydration given off. But second and third sample, I heated it and there was a negligible change of mass. That means that all the water was already gone. And so to answer this question, we're going to say that no additional mass was lost between the second and third heating, indicating that our waters of hydration had been driven off, are gone. Driven off. Okay, so if we look at that, that kind of makes sense, doesn't it? So that's explaining that lab technique. So Part B says use the data to calculate the total number of moles of water loss when the sample was heated. Okay, and so if you want the number of grams of water lost to calculate moles, we would take, looking at our data above, we would take the mass of our sample that still had water, So 25.825 grams, which is the sample and the container, minus, so that's the mass of the sample in the container, minus the mass when it reached that constant mass. So 23.977, this last mass over there, and that is the sample and container after heating. And the difference between those gives us the mass of the sample without the water, but it also still includes the container. So let's go ahead and get rid of that too. So let's go ahead and subtract the mass of the container as well. And so if we look, the mass of the empty container is 22.347, and this is just the mass of the container. Okay. So if we look at that, this will be the only difference between these. The only thing that's left are the water in the sample. We've subtracted the mass of the sample after heating. We've subtracted the mass of the container. The only thing left is water. And so that is 1.848 grams. And we don't want to know mass of water. We want to know the moles. And so our next step is to take that answer, and I'm just going to go ahead and we'll go do that right here in green. If we divide this answer by the molar mass of water, 18.02 grams per mole for water, we get a number of moles of water is 0.1026 moles. And we get 1 point here for finding the number of moles of water. 1 point here for the correct explanation. Okay. Now our next step says to determine the formula of the hydrated compound. Okay. So if we want to know the formula of the hydrated compound, we want to know essentially if we have magnesium chloride dot waters of hydration, we want to know what's this number here. I don't know how many moles of water are associated. And so in order to know that, it's kind of like an empirical formula problem. We just need to figure out the mole ratio between these two guys. So we know the moles of water. Our next step is to figure out, for this problem, we have to figure out how many grams of magnesium chloride we had to figure out how many moles of magnesium chloride did we start with. And so if we look at that, to find the mass of just the magnesium chloride, we would want to look at our final sample after it's heated. So 23.977 grams, and that's the sample and container after heating. Okay, and if we subtract just the container, 22.347 grams, we get the mass of just the dry magnesium chloride, which is 1.630 grams. So if this is the mass of the dry magnesium chloride with no water in it, we can figure out how many moles of magnesium chloride we started with. So the next step, find out how many moles. So let's do that in blue. 1.63 grams magnesium chloride divided by, if we know the molar mass of magnesium chloride, and hopefully you figured the mass of magnesium chloride, and it's 95.2 grams per mole. And that gives you 0.01712 moles of MgCl2. Okay, so now we know how many moles we started with of water, and we know how many moles we started with of magnesium chloride. So now all we have to do is figure out the ratio between the two. And so if we divide both of those by the smallest number of moles, our 0.10, and this is for our water, our 0.1026 moles, and our magnesium chloride 0.01712 moles. Our smallest number of moles is magnesium chloride, so if we divide both of those by 0.01712, now for this one, I showed you this step because you're in the midst of learning this. For your final answer, you could not do this last step and just show this one right here, this step right here. Now this one is going to be 1, and this gives us 5.993, which is essentially 6. So we have a ratio of 6 to 1 for our mole ratio, which means when we write the chemical formula for this, we have magnesium chloride, and there are 6 waters associated with every 1 mole, or for every molecule of magnesium chloride or formula unit, we have 6 molecules of water associated with this 1 formula unit. And so that's how you would do that kind of question. You would earn, let's see, 1 point for finding the number of moles of magnesium chloride, and 1 mole for getting the correct calculation here, and or getting the correct chemical formula supported by calculations. Again, as long as you're consistent with previous answers, this answer will be taken. Okay, then our last question is, if a different student heats the hydrate in an uncovered crucible and it splatters out of the crucible, or in other words, losing some of your sample, what effect will it have on the calculated mass? And it asks you to justify your answer. And so this one you would need to explain. Now, this is a 1-point question, and 1 point for the correct answer with a justification. No justification, just an answer, and you would earn no credit. So for this one, if you think about it, if you lost some of the sample, you would probably think, or if you lost some of the sample, the mass after, and I'm just going to reason through, the mass after would be less. Would be less, and therefore, the calculated moles of water. So you might think some of that mass was actually water that you lost. Therefore, the calculated mass of the hydrate, of the waters, would be too large. Some of that mass Okay, so the mass after would be less, therefore the calculated mass of water would be too large. Some of the mass of the splattered sample would be assumed to be water, but it actually had some magnesium chloride as well, so when it included the magnesium chloride as well. So here's our answer. The calculated mass would be too large. Okay, so I'm going to pause, and this is part 1 of our free response videos. Continuing on the next video.